connecting moles and gases. Okay, and this part's a little bit like it's a little bit like if you're good with numbers, you'll see it. Hopefully everybody will see it. Okay, so Avogadro's law. It directly relates gas volumes to moles. Okay, so mass and volume can be used to measure the amount in the number of moles. Okay, so what we've been doing, we have some moles and we've turned it into grams, or we have some grams and we've turned it into moles. Well, what about liters? What about milliliters? Right? Can we turn those into moles? Can I have, like, let's say I have 100 milliliters of carbon dioxide, right? Well, can I turn that into a quantity in moles? Okay, so volume is just the amount of space that something takes up. Equal volumes of all gases when measured at the same temperature and pressure contain equal number of particles. So let me do like a little diagram for you. Actually, you know what? Hold on. There's a video I can play to make more sense of this. No, the IB Thornley, not the band. So he's got, so this is another resource. He explains things really well, but he has a nice little animation of this. Let me just. Okay, let me just do my thing here. Stop presenting. Okay, so we're gonna watch a little video about this concept, okay? Short video. Long video. Okay, we'll probably watch this video and we'll be ready to go home. Okay, people at home.
Calculation.
Can you see and hear this?
Yes,
Yep.
we can.
Okay, so this is, and we'll do example. We'll do our own examples too. But like I said, if this is the video I'm thinking of, he's got a nice little animation to explain this concept.
Of reacting volumes of gases using Avogadro's law. Okay, let me just turn off the white snake. I'm in a vacuum tunnel here, and there are 4 samples of gases. Each is 1 mole of the gas. So I've got 4 grams of helium and 20 grams of neon, which is a mole of neon. Now notice how the volume of all these gases is the same. 1 mole of any gas at STP is 22.7 decimeters cubed. So each of these samples is 1 mole. Even though their masses are different, the volume is always 22.7 decimeters cubed, assuming STP. Now, Dr. Atkinson says it's 22.4. The old IB syllabus was 22.4. The new one's 22.7. IB, you can't change constants. They're constants. Dr. Atkinson, thou shalt suffer my wrath. The reason that they're in a vacuum here is because the helium, of course, would float away if there was air in the room. How else could I measure it? 22.4. It was 22.4. Now it's 22.7. Oh dear. Strangely enough, Avogadro didn't even know about the existence of atoms, but it's named in his honor of his experiments. So 1 mole of any gas at STP is 22.7 decimeters cubed, and a decimeters cubed is also a litre. STP, well, standard temperature for gases is 273 Kelvin, and standard pressure is 100 kilopascals. In the previous syllabus, it was 101 kilopascals, and that's what's causing the discrepancy. Okay, let's look at some simple questions, moving on to trickier ones. So it doesn't matter if it's carbon dioxide, carbon monoxide, sulfur dioxide, or sulfur trioxide. It's any gas this is true about. So let's look at carbon monoxide versus carbon dioxide. Well, if I have a gas, carbon monoxide, the actual molecules take up very, very little of the volume. Most of the volume of a gas is empty space. And if I turn the carbon monoxide into carbon dioxide, well, you know what? That's barely changed anything. The volume of the gas is still mostly empty space. And so that's a partial explanation as to why carbon dioxide doesn't take up more volume than carbon monoxide. Than that, but beyond the IB. So if I have 22.7 decimeters cubed of a gas and it has a mass of 44 grams, is it carbon monoxide or carbon dioxide? Well, it's a STP, so I know I must have 1 mole of gas. So which has a molar mass of 44 grams per mole? Carbon dioxide. 11.35 decimeters cubed seems an arbitrary number, but you know what? That's half a mole of gas, a STP. If 1 mole is 22.7 decimeters cubed, how many moles is 11.35? Half a mole. What's the mass? It's just simply working out the mass of half a mole of sulfur dioxide. So using the equation, mass is moles times molar mass. That gives me 32 grams. Now, like in all these videos, I don't have the time or inclination to fix the sig figs and the decimal places all the way through. You should use the molar masses on the periodic table that the IB give you, which have a few decimal places. This is the Haber process. You need to learn this equation. Produces ammonia. And so 1 mole of nitrogen needs 3 moles of hydrogen to make 2 moles of ammonia. And conversely, 10 to 30 to 20, the ratio works like that with the coefficients. But you know what? It's not just moles. It's also vols or volumes that work the same. 10 decimeters cubed of nitrogen reacts with 30 decimeters cubed of hydrogen to make 20 decimeters cubed of ammonia. Okay, so this is the contact process used to make sulfur trioxide that makes sulfuric acid to make plastics and fertilizers. You need to learn this. Let me put the values in. 6 decimeters cubed of sulfur dioxide and 8 decimeter cubed of oxygen. To find out the volume of SO3, you might be tempted to just add them up, and that's wrong. Avogadro's law says you can't do that. This is excess and limiting as well. So which is the excess and which is the limiting? Just like before, 6 over 2 and 8 over 1. Which is the lowest number there? Yeah, 6 over 2 is lower. So that's the lowest is the limiting. This is the limiting reagent. The other one's wrong. 8 decimeters cubed, that's wrong. That's too much. It's excess, excess, excess. All right, so now I know that 2 is to 6 as 2 is to 6. So I've got 6 decimeters cubed of sulfur trioxide. You can use the ratio like that. My mass of excess reactant, well, if 2 is to 6, then 1 is to 3 decimeters cubed. So I actually put in 8 decimeters cubed, but I only used 5 decimeters cubed excess. Now the question asks for the mass. So what's the mass of 5 decimeters cubed of oxygen? Well, a mole of oxygen is 32 grams and 22.7 decimeters cubed at STP. And using some cross multiplication, I can work out the mass of oxygen. Okay, for this one here, we're assuming STP in all gases. Let me put the numbers in. That's the volume of nitrogen dioxide, and 900 for the hydrogen. So I need the data for the star and the squiggle, and that should help me work out the first two. All right, excess and limiting. The volume divided by the coefficient. What's the lowest number? The lowest is limiting, so nitrogen dioxide is limiting. And so that's the number that I need. 900 is too much, it's excess, cross it out, excess. So 2 is to 227, as 2 is to 227. Okay, that's the first answer. What's my mass of water? Well, 4 is to 454, and a little cross multiplication gives me 360 grams. The volume of excess reactant, well, I put in 900, that was too much. So 2 is to 227, as 7 is to, little more cross multiplication, to get 794.5. So I put in 900, I only used 794.5, so I had 105.5 decimeters cubed excess at the end. And we're done.
Okay. So, okay, let me just stop presenting. Okay, so we finished at 10:40, right? Because they're going to start calling you guys down. So people in class.
It can't be that simple. Well, the pressure has to be in kilopascals, volume in litres or decimeters cubed, same thing. The gas constant, that looks complicated. It's in the data booklet. And temperature, we might try and mess with you by giving it to you in a unit other than Kelvin, like degrees centigrade, but it should be in Kelvin. So just add 273 if we give it to you in degrees centigrade. So let me draw out an ideal gas. Well, there is no such thing as a real ideal gas. It doesn't exist in the real world, but the equation still works really quite well. So some things you need to know about this ideal gas is that the equation assumes zero volume of gas. Now that's the atoms and the molecules themselves that has zero volume. I'm not saying that V in the equation is zero. No, that's wrong. The individual atoms and molecules have zero volume. Wow. So helium, that's really tiny. But DNA gas, well, DNA gas, that's going to be huge if it even existed. So helium's going to give better results with the ideal gas equation than a big molecule. We're also assuming elastic collisions. And that means that they don't react and they don't stick together, the molecules. They just bounce off each other cleanly. They don't stick. So again, helium, that's great. Hydrogen fluoride, that has a strong dipole, so it's quite sticky. So hydrogen fluoride's not going to give us good results with the ideal gas equation. And if I add hot nitrogen and hydrogen, well, that's going to make ammonia. No, they're going to stick together and react. That's going to give me terrible results with the ideal gas equation. If I was to increase the pressure by decreasing the volume, it's no longer really a gas so much anymore. I'm kind of liquefying it. If I push gas together, then it could liquefy. The intermolecular bonds are going to be more attractive and everything's closer together, so it's going to stick together more. It's not going to be very gassy, if you will. And if I cool down an ideal gas, what will also happen is the molecules or the atoms will come closer together as the temperature lowers. As they get slower, the intermolecular forces will get consequently relatively bigger, and so they start to clump together. The slower things go, the easier it is for them to stick together, and that's bad, because if you stick a gas together, well, that's called a liquid. And so the colder it is, the more liquidy, if you will, the gas is becoming, the more it's going to stick to each other. So let's look at an easy question with no tricks in it whatsoever. So PV equals nRT. The pressure is in the question. The volume's in the question. The number of moles is in the question. The gas constant, well, that's in the data booklet. And that just leaves me with T for temperature. Now, when I solve that, it's going to give me temperature in Kelvin, don't forget. And we're going to use 2 sig figs because it's multiplication and division. And it goes, the answer goes with the part of the question with the least sig figs. Well, that was an easy one. So this is a medium difficulty question. Let's see if we can work out R from the data that's given, and you actually have to memorize this data. So the pressure is 101, that's standard. Some textbooks say it's 100, but the data booklet says 101. Oh dear. If you get an infinity in physics, that might be okay, but in chemistry, infinities are always going to be bad. So I forgot to convert to Kelvin, right, and I fixed that up. So I get 8.29. We put the units in. The pressure gives me that, the volume gives me that, the moles at the bottom, and the temperature is also at the bottom. Now, it's not exactly the one in the data booklet, so there's been some rounding here and there with the numbers that the IB expects you to use. So this is an evil question with a couple of tricks. The first trick being, where's molar mass in the ideal gas equation? Oh, El Diablo. Even he thinks it's evil. Well, let's write it out. PV equals nRT. Molar mass. PV equals nRT. And, well, you know, the N, the number of moles is mass over molar mass, isn't it? So that's where molar mass is hidden. So let's change that to mass divided by molar mass. In fact, everything's divided by molar mass. Rearrange that to get molar mass on its own. All right, let's put the numbers in. So 15.0 grams is the mass. Gas constant from the data booklet. Temperature, well, don't forget, you have to convert to Kelvin. Adding 273 gives you that. Pressure and the volume are, now the volume is given in milliliters, you have to convert it to liters. Great, that gives me a molar mass of 71.1, 3 sig figs. Now the question says the actual molar mass is found to be slightly different. Account for this. Okay, well, you didn't use an ideal gas because there's no such thing. So what could have gone wrong? Well, maybe the molecule's a little polar and that makes it less ideal. Or maybe it underwent some sort of slight reaction and that also made it less ideal.
Okay. What's that?
Grammarly does more than catch errors. With Grammarly, you can find
Solving problems of the ideal gas law. Well, let me remind you that PV equals nRT, and that's the ideal gas law. And the assessment statement says that keep the number of moles fixed and R's a constant. So then we can assume that PV divided by T, that's nR, and if those are both unchanging, well, PV over T, that's going to be a constant for your question. No matter how you mess with P, V, and T, as long as the ratio P times V divided by T is unchanged, everything's going to be dandy. So the equation that you're going to need is P1 V1 over T1
Oh, we did this.
is P2 V2 over T2.
Okay, that's okay. We did this one. This is already in your notes. Okay, so let me just open up gas laws, and that is the note that we're going to finish today. Okay, so we've got a bunch of calculations coming up, but I do think I found a way to make them more accessible and intuitive. Okay, so 1.3V gases. If you weren't here for the tutorial, my brother bought a 3D printer, and I'm just really wondering what he's planning on doing with it. Oh, these programmers or software, whatever he does. So if I spaced out, I'm probably thinking of all the things I can make on a 3D printer. He said it was like a glue gun attached to a motor. We'll see. Okay, so this is where we finished off last time. Oh shoot, you can't see this. Okay, can everyone see the note?
Yep.
Yeah.
Good. Okay. Okay. So I'm saying okay over and over. So we have so let's just take this gas constant and just redo it a little bit. Okay, because we're going to be using a different one when we do the questions. Okay. So I have molar volume of a gas, right? So the volume of 1 mole of a gas at standard temperature and pressure. So let's use the values that were given over here, right? So P, so PV equals nRT. And we're going to isolate R. So R equals PV over NT. Okay, so R is equal to, my pressure is 100 kilopascals. My volume is 22.7 liters. My number of moles, I have 1 mole. And then for temperature, I have 273 Kelvin. Okay, so if I were to take all that, and if I were to put it into a calculator, okay, so 100 times 22.7 divided by 273. Okay, I get 8.315 kilopascals. So your units are really important here, kilopascals. DM3 is liters, mole minus 1, K minus 1. Okay, so the reason that I have a little minus 1 beside the mole is because it's a denominator, right? So if I'm taking something out of the denominator, I just give it that minus 1. The same thing with Kelvin, it would be K minus 1. So we can take this and use that as our gas constant. Okay, so we can take that and we can use it as our gas constant instead of the one we did on Friday. The one we did on Friday, I based it on your textbook, but I don't like that way. I think this makes a lot more sense. I mean, if you want to think about, you know, pressure in terms of like Newton meters or whatever, you can. Okay. So we have to stick to certain units, right? And that's where IB might try and trick you up. Like they might give you units and, you know, you might not realize that you have to convert them. Okay, so for pressure, we want to use kilopascals, kPa. Okay, so kilopascals. For volume, we want to use DM3, which is the same as liters. For number of moles, just use mole. And for temperature, use Kelvin. Okay, you saw in the video how he wasn't using Kelvin, like to derive R, he wasn't using Kelvin, and it would have given him a denominator of 0, and that is just not something that we want. You don't want a denominator of 0. Your calculator will give you a big old E. I'm sure there's many philosophical debates about, you know, what happens when your denominator is 0, but wait for calculus. Okay. Okay, so we're going to do some questions. We're going to use PV equals nRT. So a helium party balloon has a volume of 18 liters. Notice how I say liters instead of DM3. DM3 is cumbersome to say, liters is not. At 25 degrees Celsius, the internal pressure is 108 kilopascals. calculate the mass of helium in the balloon. Okay, so this is a lot of information here. So let's say I got this question on a test. Okay, so I'd read the question over. So for mass, I sort of think, well, I have a formula that gives me moles. Okay, so I have lots of formulas. So I have like, you know, Boyle's law, Charles' law, all those formulas. They don't really have anything where I can figure out mass. This formula, though, I can figure out moles. And from moles, I know how to go to mass. So I'm going to use this formula. Okay, so pressure, volume, moles, RT. Okay. Okay, so pressure, I have 108 kilopascals. So this is the right number of kilopascals. Okay, I don't need to convert anything. For volume, I have 18.0 liters, which is the right unit. I don't know moles. I'm going to figure out moles. R is a constant. So R is always, sorry, I have it. So I have 8.314 in this question. Use whatever the data booklet gives you. I don't know what the data booklet gives you. I haven't looked it up in there. Close enough. Okay, so my gas constant, and I tend to use units in these questions because they help me to see that I've put it together properly. Like if my units cancel the way that they're supposed to, I know I've set up my question properly. If my units aren't canceling, I know I messed up somewhere. Okay, my temperature is 25 degrees Celsius. That's a 5, not a 3. What do I have to do to my temperature?
Convert to kelvins by adding 227.
By adding 227?
273.
273. I think
Oh, oops.
it's okay. You're just learning, it's fine. I forget all the time how to go to Kelvin. Okay, so 25 degrees Celsius plus 273 equals 298 Kelvin. Notice with Kelvin, you just write the K, there's no degree sign. Okay, so I want to solve for moles. So moles is equal to PV over RT. Okay, so that equals, okay, so pressure is 108 kilopascals. Volume is 18.0 km3. My gas constant is 8.314 kilopascals. DM3 -1 K -1. And my temperature is 298 Kelvin. Okay. Okay, so what can I cancel? If you see something on top and the exact same thing on the bottom, you can cancel it. Okay, so what can I cancel? Good, I can cancel kPa. What else can I cancel?
Liters.
Yeah. Good. Okay, so another way that you can cancel is if you have something times per something. So I have Kelvin times per Kelvin, so I can cancel those two. And I don't see the word mole anywhere, so I'm going to be left with mole -1. But I want to be left with moles, right? I'm looking for N. So I end up getting 0.7846. Let me just, I'm gonna do this a little bit differently, okay? Okay, so I have, just for those of you, like some of you might understand this sort of intuitively, but in case you don't, okay, this is what I end up with. So that's like having 0.7846 0.7846 divided by mole minus 1. Okay, so when you have a -1 like that, 0.7846 divided by 1 over a mole. Okay, so that's what a -1 means. But when I'm dividing with fractions, I have 0.7846 times 1, which is just 0.7846 moles. Okay, so I do end up with the unit that I'm looking for. All my other units have canceled. So I have a helium party balloon, okay, and using okay, so my I have 0.7846 moles. Okay, so 0.7846 moles of helium. Okay, according to PivNerd. My question is asking me for grams, right? My question doesn't want moles, my question wants grams. My question wants grams. So what do I do to turn this into grams? I'm taking, yeah? Good. I was gonna say, I'm taking out my periodic table. That should be a hint. Okay, so mole, grams. Okay, I wanted to cancel my moles. So for helium, it's 4 grams per mole. Put that into my calculator, so 0.7846. Let me just take a look at my sig figs here. So I have 3 sig figs, 2 sig figs, 3 sig figs. Okay, so how many sig figs should my answer have?
2.
2, right? I use a nice long number, so my answer is accurate, but in the end, I round it to 2. So I have 3.1 grams of helium. Okay, so that is our first question using PivNerd. These are from your textbook. For some reason, your textbook really likes you to calculate moles in these questions, but that's okay. Like if you do a lot of them, right, you really get good at this kind of calculation. Okay, so does anybody need me to go over anything with that one? I'm not hearing any protests, so let's go to the next one. All right. Okay, so a sample of gas has a volume of 445 cubic centimeters and a mass of 1.500 grams at a pressure of 95 kilopascals and a temperature of 28 degrees Celsius. Calculate its molar mass. A lot of information. Okay, so I want molar mass. So molar mass is grams per mole. So I have grams, but I need moles, right? I need moles. And my question is telling me a volume, it's telling me a pressure, and it's telling me a temperature, right? So those are all the things that are together in PV equals nRT. So that's the formula I'm going to use, okay? So I'm gonna find my number of moles, and then I'm just gonna do grams divided by that number of moles. So PV nRT. Okay, so I've got pressure, 95 kilopascals, that's the right unit. Got volume, 445 cubic centimeters. Okay, what do I need to convert that to?
Decimeter cubed.
Right, to liters. So I need to convert it to liters. But here's what I do all the time. I forget the conversion factor. I forget how many cubic centimeters, how many CM3s are in a DM3. So this is a little thing I do. I like figure it out as I go. Okay, so 1 DM is 10 CM. So if I cube this one, okay, I cube this one, I have to cube this one. So that means 1 DM3 has 1000 CM3s. That's what I do. And then I can set up my conversion factor. I'll show you what to do like as a shortcut, but let's just set up the conversion factor this one time, just in case you forget like I do. Times, okay, so I want DM3s, not CM3s. Cancel. So 445 divided by 1000 is 0.445 DM3. And your shortcut is taking that decimal and moving it 1, 2, 3 places to the left. Okay, which is what I will be doing from now on. Actually, no, who am I kidding? I'll probably forget again. I have to do this whole procedure again. Okay, so for volume, I have 0.445 DM3. Moles is what I'm trying to find. My ideal gas constant is 8.314 kilopascals times liters. One, K minus 1. And my temperature, so 28 degrees Celsius plus 273 is 301 Kelvin. Okay. So again, because I forget, like I know Pivnert, but to figure out for N, like I have to rearrange it. Okay, so I'm going to do this in a different color. Okay, so N equals PV over RT equals, all right? So same thing we did last time. So pressure, 95 kilopascals, volume, 0.445 PM3, R is 8.314 kilopascal, DM3, mole minus 1, K minus 1, and then 301 Kelvin. So now I start canceling to sort of check that I've subbed everything in properly. So kPa and kPa, DM3 per Kelvin and Kelvin. Okay, and now I just put this into my calculator. So how many moles do I have? I have 0.01689 moles. Okay, so 1.5 grams of this gas has 0.01689 moles. So to find my molar mass, okay, that's grams per mole. So 1.500 grams over 0.01689 moles equals 88.8 grams per mole. Okay. So what's my mistake? Can I leave it at 88.8? Right, sig figs. So how many sig figs should I have in my answer? 2. Good. So it's 89 grams per mole. Oh, that just got really big. Okay, I'm just gonna do this manually. I'm trying to use the trackpad on my gamer computer. I'm like the least gamer person there is. Mind you, I did spend a fair bit of time on Animal Crossing yesterday. It was Turkey Day. I helped the turkey cook. Okay. Another question with sort of another layer of difficulty here. You're given density. You're given a density. So a gas has a density of 1.65 grams per liter. This should have a little slash. At 27 degrees Celsius and 92 kilopascals. Determine its molar mass. So I have EVNRT. Okay. As soon as I'm given a gas question, it's talking about mass. I'm thinking Pivot, right? Because I connect moles to the mass. So if I start filling this in, well, I've got 92 kilopascals of volume. I'm not given a volume. I'm not given moles. R is always 8.314 kilopascal. 3, this one, K minus 1. 27 degrees Celsius plus 273 equals 300 K. Well, what am I going to do about volume? Does anybody see my unit for volume?
You would have to get it from the density.
Good. You'd have to get it from the density. So my density is 1.65 grams per liter. Okay, so I'm going to assume that I have 1 liter of gas and do my calculations based on that. Okay, so my volume is 1 dm3. Okay, so now again, I'm finding moles because I need to find molar mass, right? Which is grams per mole. I have grams, so my 1 liter of gas weighs 1.65 grams. Now I just need to find how many moles are in that 1 liter of gas. So cheating, N equals PV over RT. Okay, so pressure 92.0 kilopascals. Volume is, where's volume? Volume is 1 dm3. Okay, 8.314 kPa dm3 minus 1 K minus 1 and then 300 K. Okay, so my kelvins cancel, my dm3 cancels, my kilopascals cancel. So I have 0.03689. Okay, so I have the bottom part to this, I have the top part to this, so now I can just divide them. Density equals 1.65 grams over 0.03689 moles. Density, what am I doing? No, molar mass. M. And that is equal to 4.73 gram per mole. Okay. 3 sig figs, 2 sig figs, 3 sig figs. So I want this to be 2 sig figs. So it is equal to 45 grams per mole. Okay, let me just rotate my wrist. Okay, so I think that we're on our last question. So it's another one of these experiment questions that you're given, which I think we did in the tutorial too. We did an experiment-based question. So something like this, like I might give you in the application section of your evaluation, which I think is coming up next week. So your evaluation for topic 1. I have yet to figure out how to use Google Forms for chemistry. Honestly, I don't think you can because you have to like write out your calculations. So I don't think I'm going to use the Google form. I don't know if that makes you happy or not. But I don't know how you can possibly type something like this. So it would be very cumbersome. Okay, so experiment to calculate the molar mass of carbon dioxide by application of the ideal gas equation. Okay, I think I have to draw for you here. So a known mass of copper 2 carbonate is heated and the gas evolved collected by displacement of water. So you'd have your test tube, you would have your CuCO3, you would heat it with a Bunsen burner. Thank you, COVID. I don't have to teach you how to use a Bunsen burner. They're scary. I don't like them. You'd have to heat it. Okay, you'd have a cork with a little straw going through it. Then your straw would go into some water. Okay, it would be in some water. You'd have a upside down being held up by some kind of magic. Upside down. Okay, and then your gas would displace the liquid. So here you would have gas. Okay, so you measure how much gas is given off by this reaction. Okay, so your gas is being given off, it's being collected here. So your copper carbonate turns into CuO. CuO becomes, okay, and this is your amount of gas given off. So your mass of the boiling tube and CuCO3 before heating, 33.910 grams. Okay, so this is, I'm not going to do that. Okay, so your mass of the boiling tube and copper 2 carbonate after heating, 33.822. So this is without carbon dioxide. So your carbon dioxide is gone. Okay, so we want to figure out how much carbon dioxide was given off by this reaction. How would I figure that out? No? Okay, so you would subtract. You subtract your two numbers. So I have 33.910 minus 33.822. Let me just, I think I'm looking at the wrong thing on my paper. Hold on. Okay, so 33.910 minus 33.822, 0.088. Ugh, sig figs are going to be awful. So I have 3 decimal places. Okay. Okay. So now what I need to find is I need to find the molar mass, right? So I have this amount in grams and I need to find the amount in moles of my gas. And then I'm going to do grams per mole. So the volume of gas collected, so I have measured this amount to be 38.1 cubic centimeters. Okay, do you remember what we do? So we have P, B, N, R, T. Okay, P, B, N, R, T. So for pressure, you'd look it up, 101.3 kilopascals. For volume, that's part of your experiment. Okay, number of moles we're going to calculate. R is 8 point. And temperature is 293.0 Kelvin. Okay, what's my shortcut? Do you remember my shortcut to go from cubic centimeters to right? Move the decimal point 3 places. 38.1, 1, 2, 3. So equals 0.0381 dm3. Okay, so now, and again, I forgot. Okay, so N equals PB over RT equals 101.3 kilopascals. My volume is 0.0381 dm3. 8.314 kPa dm3 mole minus 1 K minus 1, and then 293.0. Okay. Okay, so I put all of that into my calculator and I get 0.001584 moles. Okay. Okay, so I want molar mass, right? So molar mass is grams per mole is equal to 0.088 grams, 0.001584 moles, 0.0. So 55.5 grams per mole. Okay, so I'm going to show you how to do another. This is just systematic errors. So the mass of carbon dioxide is a lot bigger, a lot smaller than this. What's the mass of carbon dioxide? Okay, so the mass of carbon dioxide I think it's 44.01. It's 12.01 plus 2 times 16. 44.01 grams per mole. Okay, so I'm way off, right? Like I can calculate a percent error. I'll show you how to do that, but let's just think about like, so it's almost like I have collected, or like something's off with my numbers, right? So what can be off? Well, the gas collected might not be pure carbon dioxide, so something else might have gotten in here to give me a bigger measurement. Okay, the carbon dioxide might be soluble in water, so maybe the carbon dioxide that I'm producing maybe some of it gets dissolved in the water and not all of it gets collected up here. I can collect air in the tube with the gas, or the gas collected has not equilibrated to room temperature. I'm not sure what that one means. Maybe it's like still really hot, so it's spread out more than it should be, and it's taking up more space in my tube. Okay, so I'm going to show you another calculation. It's called percent error. So I'm going to do it in a different color. So percent error equals, okay, the absolute value of your accepted minus experimental over accepted. Do we all know what an absolute value is? I don't know if you learned that in math. An absolute value always gives you a positive number. Okay, so percent error. Okay, so my accepted value, my published value is 44.1 minus my experimental, which is 55.5, divided by my accepted, which is 44.1. Oh, and of course, you have to times by 100. Times 100 equals 26.1%. Okay, so that's my percent error, 26.1%. I'm off. Okay. Okay, so that is, I believe that's it for PivNote. And now we are going to go somewhere very theoretical. And I'm going to try and explain it as best as I can. I'm not so good with words, though. Sometimes I'm not very good with words. Again, and this is from your textbook. So if I was just intuitively explaining this concept to you, sorry, I just put. Okay, so if I was intuitively explaining this concept to you, I might explain it differently, but I was inspired to follow along with your textbook when I was making the notes. Not always the best laid plans to go along with the text. Sometimes it's a really good textbook, but sometimes it's just like there are things that are left out. Okay, so remember we were talking about ideal behavior, and we make these assumptions for an ideal gas, right? We have to sort of assume certain things for the gas, which you can hear me flipping papers because I'm looking for these assumptions. So we have to, for PivNert, for our equation to work out, we have to make some assumptions about the gas. Okay, so what were these assumptions? So I think there was two of them, right? So our assumptions for an ideal gas. Okay, for PivNert to work, these are properties your gas has to have. Okay, so your particles have negligible volume. Okay, so your particles have negligible volume. And there are no interparticle forces. Okay, so particles, negligible volume, and no interparticle forces. So these are your assumptions. I mean, I think there's more than those, but these are the ones that we're going to work with. So those are your assumptions for an ideal gas. Okay. So textbook thing, I'm going to try and explain it to you. Okay, so let's say I have 1 mole of an ideal gas. Okay, so I have 1 mole of an ideal gas. Okay. So okay, so however I change my pressure, my other quantities will change in such a way that I always have 1 mole. Okay, so based on pressure, for 1 mole of an ideal gas, PV over RT will equal 1. Okay, so for 1 mole of gas, the relationship PV over RT equals 1. Okay, so 1 mole of an ideal gas. So if I compare, so this is how I want you to sort of look at this graph. Okay. Sorry, I'm just gonna get the textbook for a minute because I forgot what I'm supposed to put into this blank. Ideal gases, where are you? Real gas. I think it's real gas. Okay. Okay, so the way that I want you to look at this graph, so you have 3 different gases, right? You have 1 mole of 3 different gases. Are those gases behaving like an ideal gas, right? Well, they're behaving like an ideal gas if they're matching this line, okay? So what we can see is that, let's look at temperature first. Okay, let's look at temperature first. So ignore the pressure, ignore the PV over RT. My gas behaves like an ideal gas if it's close to that line. Okay, so here is, I have 3 gases, 1 mole of each. Notice how my 1000 Kelvin gas is the closest to the line. Well, that's saying that my real gas behaves like an ideal gas at higher temperatures. Okay, so a gas behaves most like an ideal gas at high temperature. Right? And just because it's like the closest to the line when the temperature is the highest. Okay, so in terms of temperature, when I have a low temperature, well, that's when I'm deviating from ideal gas behavior the most. Okay, so at low temperature. Okay, so that is temperature, right? My gas behaves most like an ideal gas at high temperature. Well, let's break that down. Why would your gas behave like an ideal gas at high temperature? Okay, so if you think about it, and I think this is, I think we fill it in here, so I'm just gonna like tell you. Okay, when I have a high temperature, my gas particles are just zooming around, right? They're zooming around, they're really, really fast. That means that they have less attraction to each other when they're zooming around like that. So your condition of no interparticle forces is met when you have a high temperature. Okay, let's take a look at pressure. So again, ignore that. So just pressure. So my pressure Well, especially this one, right? Especially like this red one, it really behaves like an ideal gas at low pressure. Okay, so notice my curves are closer to the line at low pressure, and the higher the pressure gets, the farther away they get from the line. So we would say that a gas behaves most like an ideal gas at low pressure. Okay, and shows the greatest deviation at high pressure. Well, what's going on with pressure? Okay, so for pressure, this is how I think about it. So when I think of low pressure, okay, when I think of low pressure, well, when I have a high volume, I have low pressure. Okay, so I have a high volume. When I have a high volume, my gas particles have more space. So my gas particles take up less space. Okay, so my gas particles take up less space when I have low pressure, because when I have low pressure, I have a high volume. Okay, so my first condition is met. Okay, particles have negligible volume, right? Negligible volume, take up no space. Okay, so that's why I would have ideal behavior when I have low pressure. Okay, so let's fill in the blanks. I don't know if we'll finish this note today, but we could finish it on Monday. Okay, so what happens at low pressure and high temperature for a gas to behave like an ideal gas? Remember when we first defined an ideal gas, we stated that it would have particles with negligible volume. So it just means up they're not taking up any space. Negligible volume. And no interparticle forces. Okay, so at low pressure, and high temperature, conditions occur so that gas particles come very close to having no volume and no interparticle forces. And I doubled this. Ugh. Let me just erase this. I wasn't paying attention, which is like my whole life. It's the story of my life, not paying attention. Okay. So let's talk about the volume of gas particles being negligible. I might just fill in the blanks and then just go over it. Okay, so at low pressure, the volume is large. So the gas is very spread out and occupies a large space. The gas particles are very tiny and take so little of that space that they can be considered to have negligible volume. Okay, so as the pressure increases, the gas occupies less space and the gas particles will occupy a greater proportion of that space. So they have volume now. The gas particles occupy enough space at this point that their volume can no longer be negligible. So at high pressure, the volume of a real gas is larger than that predicted by the ideal gas law. So this is something from your textbook. So PV over nRT is greater than 1. Okay, it's 2:18. I'm not gonna, do I want to? Do I want to? You're probably saying, no, miss, you should stop right there. Okay, it's 2:19. I'm going to stop.